Now we will consider uniformly charged sphere. Until now we considered the shell, and now we will consider the charge is distributed throughout the sphere, but it is considered as uniform distribution. In that case, we can write uniformly, we can write charged sphere. Okay. However, it is practically, if it is conductor, then that is not, though this type of condition is probably not possible. Anyway, let us try to work out with this as well. So for this case, again we have to consider, draw same figure here of radius A. Consider any surface of less than A radius, more than A radius. Here charge is distributed uniformly throughout the body of the sphere. The consideration is that it is uniform. So it is very difficult to visualize it. Okay, this is internal Gaussian surface. This is next Gaussian surface that we considered outside. The surface will be considered by itself. So let us start discussion in this case as well. First thing that should be clear, the charge in if rho is the charge density of this, then the charge enclosed we can write, closed will be rho v, and the total volume. Okay, so this thing should be clear. And volume in the case of spherical body is how much? 4 by 3 pi r cube. R is A here, so 4 by 3 pi A cube. Okay, and the flux will be d dot ds. Okay, and d, the direction of d will be in the direction of radial vector, and ds will be also normal to the radial vector, normal to the surface. That will be exactly same as the direction of d. So the dot product will give you 1. So only area will be left, and spherical area will be 4 pi r square. Okay, so this will be the flux, and we know that flux will be equal to the d into area will be equal to the charge enclosed. Okay, now simplify this. From here we can say 4 by will be cancelled out. It will be volumetric density, charge density, A by r square. Okay, if we consider the case when r is less than A, the first case r is less than A, then here d will be rho v r cube divided by r square. It will give you rho v r. Okay, and E will be rho v r by epsilon. This is first term to us now. If we will consider r is more than the radius of the sphere, then in that case, okay, r will be equal to the A. In that case, the d will be rho v A and E will be rho v a by epsilon. Okay, if r is greater than a outside, then the d will be rho v a cube by r square, this is constant, and E will be rho v a cube epsilon r square. So in this way we have electric field in different conditions in the case of uniformly charged sphere. Okay, I think we are missing some. Yes, here should be 3. In every denominator it should be 3. Okay, now it is okay. Let us try to plot it. Again, this is our position from the center of the spherical charged body. Here it is E. Then from center of the sphere to the radius of the sphere, it is varying when r is less than a. Up to the a, it is varying proportional to r. So there will be linear variation. Okay. At r, this is constant, everything is constant. So it is the maximum value, that is rho v a by 3 epsilon. This is the maximum at the surface. And as we move away from the surface, E is proportional to 1 by r square. See here, this is constant. So outside of this, E is proportional to 1 by r square. So in case of uniformly charged sphere, the characteristics of the electric field with the position of the point of interest is this. In this way we find the Gauss law helps to determine E and D for different cases of the distribution of the charges. Either it is point charge or any type of the uniformly distribution of the charge. Now this is the end of Gauss law. We will try to discuss the electric potential energy next. So based on the study of the charge enclosed and the flux through the surface, we will try to solve one example that is based on volume charge density. The problem is given as, if the function is given in x, y, z coordinate, the field is given as D is equal to this coulomb per meter square. Now we have to find the volume charge density at this point. The second thing, the flux through the cube of length 1 unit and the total charge enclosed by the cube. So let us start. We know the flux is equal to d dot ds for enclosed surface, that is equal to the charge enclosed, and for volume charge density we can say it is equal to rho v dv. We have this. So from here we can have this relationship with us. The first one, and second relationship, that is from the divergence theorem, we have d dot ds for any closed surface is equal to the divergence we can have, and if we relate this term and this term, then what we can find, this is equal to this. So from here we can write rho v. This is also known as Maxwell equation in integral form and in differential form. So we have the another relationship. Keeping these all relationship in our mind, let us start the solution of the problem. The first is to find the volume charge density. So for that case we have to find del dot D, that will be volume charge density. So find del over del x, this is ax, ay, az in Cartesian coordinate system, dx plus del over del y dy and plus del over del z dz. It will give us rho v. So go ahead and try to differentiate the x component with respect to x. It will give us 2y square plus z plus del over del y 4xy plus del over del z dz. dz is this x. Okay, after differentiation we will get, this will be considered as constant if we are doing partial derivative, so it will give us 0. Here we will get 4x and here we will get 0. So we have to find rho v at -1, 0 and 3. So put the value of x is equal to -1, y is equal to 0 and z is equal to 3 in this one. From there we will get rho v -4 coulomb per meter is cube due to the volume charge density. So for part A, the correct the answer will be -4 coulomb per meter cube. Let us try to part B. The flux through the cube, and we know the flux is nothing but the charge enclosed. So rho v dv, this is the charge enclosed and that is the total flux. So rho v is how much? 4x. 4x dv can be changed as dx, dy and dz in Cartesian coordinate system, where the limit of x and y and z can be 0 to 1, 0 to 1 and 0 to 1 respectively. Okay, so it should be 4x square by 2 from 0 to 1, y from 0 to 1, z from 0 to 1. In this way it will be 2 into 1 into 1. So in this way it will be charge flux should be 2 coulomb. That is the total flux through the cube. Okay, and the C part, the total charge enclosed by the cube is flux is equal to Q enclosed, and Q enclosed is total charge enclosed. So Q enclosed will be 2 coulomb. Next problem, we have D is equal to Z rho cos square phi in the direction of AZ coulomb per meter square. Calculate the charge density at 1, pi by 4 and 3, and the total charge enclosed by the cylinder of radius 1 meter with Z is equal to minus 2 to 2. So from here, the first thing that we can conclude is it is in rho phi z, it means cylindrical coordinate system, and in that there is no rho component, only charge distribution is varying in the z direction, and that is from minus 2 to 2 meter. So according to the Gauss theorem, the charge can be written as, the flux can be written as the charge enclosed, that is d dot ds. We know this for the full surface. So as we are talking about the cylinder, full surface is including the top surface, bottom surface, and the curved surface. So in this way, for closed surface we can write d dot ds, and this will be for, okay, in this way we can write for the top, for the curved, for the bottom, d dot ds. We can write this for full closed surface, we can write like that. This is ds. Okay, so in this way, this will be flux from the top, flux at the curved surface, and flux at the bottom surface. Okay, so let us come to D. D is varying in the direction of, D is a component of AZ only, whereas A rho and A phi both are, A rho component is 0. So A rho component is 0 means there is no flux due to this in this direction. So what will be that? The curved surface will not have any contribution. The flux will be at the top and bottom only. Now try to find phi t. Phi t can be written as d dot ds at the top. Now we have to find the ds component in the direction of d, that is d is in az direction only. So ds in the direction of az, to find that just write dl, it will make our problem easier. So dl in cylindrical coordinate system we can recall, that is d rho in the direction of a rho, rho d phi in the direction of a phi. If we can remember, then it will make our problem easier, az. If I am right, then this is dl in case of cylindrical coordinate system. And to find the component in az direction, just we will multiply these two, and the cross product of these two will give us az. So ds in the direction of az will be rho d phi. Okay, hopefully it is meaningful. So put the value of ds here, and d from here put it here. So we will put flux from the top surface will be equal to the z rho cos square phi rho d phi. Okay, and rho is varying from 0 to 1 by cylinder of radius 1. So the rho is 1, and the phi we know it varies from 0 to 2 phi. So in this way we can find the total flux from the top surface. Just the next thing is to integrate this, and if we will integrate this, then we will find the z is constant, that is constant, the value of z is minus 2, z is equal to 2. For top surface it is 2 and for bottom surface is minus 2. So the z is 2. Now solve this. T will be 2 rho cube by 3 0 to 1, and cos square phi can be 1 plus cos 2 phi, 1 plus cos 2 phi by 2 integration cos square theta plus sin square theta, cos square theta minus sin square theta, 1 minus it will be, this is cos square phi integration with respect to phi. This is the total answer. So let us continue. Rho cube by 3, from here it can be phi plus sin 2 phi divided by 2 divided by 2, 0 to 2 pi. Now 0 to 1, 2 1 by 3 times 2 pi plus sin 4 pi will be equal to 0 minus 0 minus 0 divided by 2. It is 2 pi divided by 2. So overall it will be 4 pi divided by 6, that is 2 pi divided by 3 from the top surface. Similarly, from the top it is 2 pi by 3, and that is rho d, and for the bottom surface ds will be just opposite to this, and ds will be minus of this, ds will be minus rho d phi az, because az will be in the minus direction. And here if we will put the value of this in the phi b, then it will be z rho cos square phi rho d phi with minus sign integration of rho from 0 to 1, phi from 0 to pi, minus with minus az direction, and here the z value is minus 2. Okay. So if you put z is equal to minus 2, then because the bottom surface lies at z is equal to minus 2 and the top surface lies at z is equal to 2. So for this z is considered as plus 2, for this z is considered as minus 2, and when we will put this, then minus 2 will be here and it will be plus 2, and remaining thing will remain same as it was in the previous case. So my plus 2 times same quantity, so it will be flux in the bottom side, it will be equal to the again 2 pi by 3. So total flux will be 2 pi by 3, that is top, 2 pi by 3, that is phi b, and plus 0 due to the curved surface, and including all it will be 4 pi by 3. So the total charge enclosed by the cylinder will be total flux, that will be the charge enclosed. So in this way the charge enclosed will be 4 pi by 3 coulomb. And still charge density is required to find, and from the previous question and from the study we know del dot D will give us rho v, and if we will proceed then the derivation in the z direction will be there only, and in the z direction derivation with respect to z it will give you rho cos square phi. Remaining quantities will be considered as constant, only z will be differentiated, and it will be at if we put the value of 1 pi by 4 and 3, then it will give us rho is equal to 1 into cos pi by 4 is equal to 1 by root 2, 1 by root 2 square is equal to 1 by 2. There is no z, so the charge density will be half coulomb per meter cube. So this is charge density. Let it make more clear.